These examples go with lesson 9.1, inference about the difference between two means, independent samples. Example 1. A sample of students is enrolled in a speed reading class. Each takes a reading test before and again after the class. The two samples of scores are compared to determine how large an improvement in reading and speed occurred. Are these samples independent or paired? Well, since it's the same student who has taken the test both before and after, we can consider these samples to be paired. Example 2. A sample of students is enrolled in an online statistics class, and another sample is enrolled in a traditional statistics class. At the end of the semester, the students are given a test. The scores from each sample are compared to determine which class was more effective. Are these samples independent or paired? Since we're talking about two different classes that are actually independent of one another, we can consider these samples to be independent. Example 3. A test was made of the null hypothesis mu1 is equal to mu2 versus the alternate hypothesis mu1 is greater than mu2. Independent random samples were drawn from approximately normal populations. The sample means were x bar 1 equals 6.8 and x bar 2 equals 4.9. The sample standard deviations were S1 equals 1.6 and S2 equals 1.3. The sample sizes were N1 equals 12 and N2 equals 10. Part A, find the value of the test statistic. All right, let's remember what our formula is for our test statistic. It's going to be x bar sub 1 minus x bar sub 2 minus mu sub 1 minus mu sub 2. And this is going to be divided by S1 squared divided by N1 plus S2 squared divided by N2. And we're going to square root that right there. Okay, and I believe they have given me all of the information that I need to plug into the formula and find my test statistic. Okay, well, let's talk about this piece right here before we plug in our numbers. Mu1 minus mu2. If the null hypothesis is true and mu1 and mu2 are equal to each other, then this part of the formula is just going to cancel out and give me 0. So essentially, all we really need to worry about in the numerator here is the x bar 1 minus the x bar 2, because we would just be subtracting 0. Okay, so we're going to have 6.8 minus 4.9 up here in the numerator. And then in the denominator, we will have 1.6 squared divided by 12 plus 1.3 squared divided by 10, and then we are supposed to square root that right there. So let's plug this into the handy dandy calculator and see what we get. And this is going to give me 3.0728. All right, so our test statistic 3.0728. All right, part B, we're to find the number of degrees of freedom. Well, remember, the degrees of freedom is going to be 1 subtracted from the smaller of our sample sizes. N1 is equal to 12, N2 is equal to 10. Therefore, our degrees of freedom will be 10 minus 1, or 9. Now, I could pull up table A3, and we would be looking on line 9 for 3.0728. So line 9, 3.0728, and it's going to fall in between 2.821 and 3.250, which means I'm going to be looking for an interval for my p-value. So instead of doing that, I think I'm going to pull up the ALEKS calculator, and I'm going to do it this way. All right, we are going to be doing a t-test, and our t-value was 3.0728, and the degrees of freedom was 9. And let's have this calculated. This gives me 0.0066. All right, part D, we're supposed to interpret the p-value. Are we going to reject the null hypothesis at the 0.01 level? We are going to reject the null hypothesis. And the reason we're going to reject the null hypothesis is because the p-value that we found is actually less than the alpha level that they gave us. And there's our statement right there. We're going to reject our null hypothesis because our p-value 0.0066 is less than our alpha value 0.01. Example 4. A test was made of the null hypothesis mu1 is equal to mu2 versus the alternate hypothesis mu1 is not equal to mu2. Independent random samples were drawn from approximately normal populations. The sample means were x bar 1 equals 73.9 and x bar 2 equals 71.8. The sample standard deviations were S1 equals 4.2 and S2 equals 3.8. The sample sizes were N1 equals 23 and N2 equals 17. Part A, find the value of the test statistic. All right, so we talked about the formula to find our test statistic on the previous example. So let's just go ahead and fill in our numbers. We're going to have x bar 1 minus x bar 2, and we're going to divide this by S1 squared over N1 plus S2 squared divided by N2. And then we're supposed to square root all this. All right, let's throw this in the calculator and see what we get. And this is giving me 1.6518. All right, there's our test statistic. Part B, find the number of degrees of freedom. Our sample sizes are 23 and 17. And remember, the degrees of freedom can be found using the smaller of the two sample sizes. In this case, 17 minus 1 will give us 16 degrees of freedom. Part C, find the p-value. We can pull up table A3 and look on line 16 and hope that we find 1.6518. Line 16, 1.7, 1.3. So it's not in the table. I'm going to pull up the ALEKS calculator again and do it that way. Let's clear this one out. We are doing a t-test. 1.6518 with 16 degrees of freedom gives us 0.0590. Let's keep in mind that we're doing a two-tailed test here, and so the 1.6518 is right here. And the area that we just found was 0.0590. And remember, by the miracle of symmetry, there's a negative 1.6518 down here that also has an area of 0.0590. And our p-value, remember, is supposed to be the sum of both of those. So we're actually going to have to add another one on here. And this is going to give me 0.1180. So our p-value is going to be 0.1180. Part D, we're going to interpret that p-value. Do we reject the null hypothesis at the 0.05 level? Well, no. We're not going to reject the null hypothesis because the p-value that we found is actually greater than the alpha value that they gave us. And there's our statement right there. No, do not reject the null hypothesis because 0.1180, which is our p-value, is greater than 0.05, the alpha value. Example 5. A sample of 87 one-year-old spotted flounder had a mean length of 126.31 millimeters, with a sample standard deviation of 18.1 millimeters. And a sample of 132 two-year-old spotted flounder had a mean length of 162.41 millimeters, with a sample standard deviation of 28.49 millimeters. Construct a 95% confidence interval for the mean length difference between two-year-old flounder and one-year-old flounder. All right, let's write down the things that we know. We have one sample that has 87 of the flounder in it. The mean length for the flounder in this sample is 126.31 millimeters, and the standard deviation that goes with that sample is 18.10. We have another sample of flounder that has 132 in it, and the mean length for these is 162.41, and the sample standard deviation for this sample is 28.49. And they also told us we want our confidence interval here to be 95%. All right, the first thing we're going to need is we're going to need that point estimate. And that's going to be, I'm going to subtract, I'm going to do x2 minus x1 so that I have a positive number here. So we're going to do 162.41 minus 126.31. And let's see what we get. And this is giving me 36.1, so there's our point estimate. All right. The degrees of freedom is going to be the smaller of the two sample sizes minus 1. So our sample sizes are 87 and 132. Looks like we're going to be doing 87 minus 1, or 86 degrees of freedom. All right. Now we want to go grab our critical value. We're going to pull that off of table A3. We want to be on line 86 at the 95%. Let's see if this table even has a line 86. And it does not. And when that happens, we are supposed to round down to the nearest number that actually appears in my table. So 80 is going to be the next number that's in my table that's less than 86. And then we're going to read across line 80 here to the 95% column, and that gives me 1.990. So there's our critical value, 1.990. we need to have the standard error. The standard error is just the bottom half of the formula for the critical value or the t-value when we were doing the p-value method just a second ago. But here it is. We're going to do the first standard deviation squared divided by its sample size plus the second standard deviation squared divided by its sample size. And remember, I switched these around so that I could have a positive number, so I did x2 minus x1. So I'm going to be switching these two as well. In the denominator here, it's not going to make any kind of a difference, though. Okay, so that's going to be 28.49 squared divided by its sample size plus 18.10 squared divided by its sample size. And we're going to square root that. All right, let's put this in the calculator and see what we get. And this is giving me 3.1488. Okay, now I'm running out of room down here, so I'm going to start working up here. We need a margin of error, and the margin of error is our critical value, 1.990, times our standard error that we just found, 3.1488, and this is going to give me, 6.2661. All right, so when we go to find our confidence interval, we're going to take our point estimate, 36.1, and we are going to subtract the margin of error, and then I'm going to round this off to one decimal place. No, I'm not. I'm going to round it off to two decimal places because all of my original data was rounded off to two decimal places. I am also going to take my point estimate and I'm going to add the margin of error, and again I'm going to round my answer off to two decimal places. And here, when I subtract the point estimate minus the margin of error, I have 29.84, and when I add the point estimate plus the margin of error, I get 42.36. So my confidence interval goes from 29.84 to 42.36. And that is our 95% confidence interval. Example 6. The mean speed for a sample of 39 cars at a certain intersection was 26.50 kilometers per hour with a standard deviation of 2.37 kilometers per hour, and a mean speed for a sample of 142 motorcycles was 37.14 kilometers per hour with a standard deviation of 3.66 kilometers per hour. Construct a 99% confidence interval for the difference between the mean speeds of the motorcycles and the cars at this intersection. Alright, let's record the information that we know. We have a sample size of cars that is 39, and the sample mean for the speeds of those cars at this intersection is 26.50, and the standard deviation is 2.37. And then we have another sample which has 142 motorcycles in it, and their average speed is 37.14 kilometers per hour, and the standard deviation on that sample is 3.66 kilometers per hour, and our confidence level is 99%. First thing we want is our point estimate. (142 minus 39). That's going to give me 103. No, I just did the ends. I did not do the means. I'm sorry. Let's see if we can get rid of this. let's start over on. All right, the point estimate is going to be our mean subtracted. So this is going to be 37.14 minus 26.5. And again, I'm subtracting x2 minus x1 because it's larger and I want to have a positive number here. All right, in the calculator, we're going to get 10.64. The degrees of freedom comes from the smaller of the two samples. That's going to be the 39, so we're looking at 39 minus 1, or 38 degrees of freedom. The critical value, coming off of table A3, we're going to be on line 38 and the column 99%. And we do have a line 38, so we're going to read across until we get to 99%. There it is. That looks like 2.712 for our critical value. All right, next thing we need is our standard error. Our standard error is the standard deviation squared divided by its sample size plus our other standard deviation squared divided by its sample size. And then we are going to square root all of that. So let's put this in the calculator and see what we get. And this is giving me 0.4882. All right, let's get our margin of error, which is our critical value, 2.712, times our standard error of 0.4882. All right. And this gives me 1.32399, but if we round that up, it's going to be 3240. Now to get to our confidence interval, we're going to take our point estimate and we are going to subtract the margin of error. And then we are going to take our point estimate and add the margin of error. And I am going to round my answers to 2 decimal places since my data here has also been rounded to 2 decimal places. Subtracting the margin of error from our point estimate gives me 9.32, and adding the margin of error to our point estimate gives me 11.96. Therefore, our 99% confidence interval goes from 9.32 to 11.96.